Nice to meet you. I'm Khadar Chokpai and you're watching my YouTube channel School of Advanced Chemistry. Today I'm going to discuss new topic that is Le Chatelier principle. Le Chatelier principle is basically applicable in reversible reaction at the stage of dynamic equilibrium, and it belongs to the physical chemistry, especially for the Cambridge A level and O level chemistry students. Let's talk about it. First of all, what is the Le Chatelier principle? Le Chatelier principle, that is explaining the effect of concentration, effect of pressure, effect of temperature on the yield of the chemical reaction when a reversible reaches at the stage of dynamic equilibrium. So, during the course of a reversible reaction, we can check the effect of concentration, change in concentration. We can check the effect of change in pressure. We can check the effect of change in temperature, and we can disturb, we can shift, we can change the position of that dynamic equilibrium. That is explained by a principle that is said to be Le Chatelier principle. Reversible reactions, what are the reversible reactions? The reversible reactions are the reactions those are proceeding in both direction, in forward direction as well as in backward direction. And these sort of reactions are expressed basically by two half arrow. That is the forward direction reaction, that is the half one arrow, and this one arrow is going to represent the reverse or the backward reaction. So this is the symbolic representation of reversible reaction, and the next phenomena is dynamic equilibrium. During the course of a chemical reaction, those are reversible reaction. After some time, after some time interval, there is the dynamic equilibrium. What is the dynamic equilibrium? Let's see over here. Number one, in a closed vessel, in a closed container, a stage comes in a reversible reaction at which the rate of forward reaction, the speed or the rate of the forward reaction becomes equal to the rate of the backward reaction. I mean, when the reactions are moving in opposite direction, one is said to be forward reaction, other one that is going to start after some time, after some time interval, you can say, that is said to be the reverse reaction. A time will come when the rate of the forward reaction or the speed of the forward reaction is equal to speed of the reverse reaction. This stage, this state, this status is said to be dynamic equilibrium. At this stage of dynamic equilibrium, the amount of the reactant and the product, that is also known as yield, product is also known as yield, become constant. I mean, there is no further net change or the further change is observed after the time when the dynamic equilibrium is arrived. So after the arrival of dynamic equilibrium, there is no more increasing the product, there is no more decrease in the reactant. So at this stage, at this dynamic equilibrium state, actually reaction is completed. So why it is said to be, and you can say that why it is said to be a dynamic equilibrium, but reaction, the reason is, but reaction does not stop. As reactions is keep on moving, it is not going to stop. So it will remain, or it remains in motion until unless it is kept in a sealed container. If you are keeping that reaction mixture in a sealed container, if the reactants are there, if the products are there, then this reaction will keep on moving for good, you can say. And that's why it's said to be the dynamic equilibrium. Equilibrium in sense that the speed of the reaction, forward reaction, or for rate or the speed of the forward reaction is equal to the rate of reverse or the backward reaction. F of forward or for reverse, rate of forward reaction, the magnitude of rate of forward reaction becomes equal to the magnitude of rate of reverse reaction. This stage is said to be dynamic equilibrium in reversible reaction. Dynamic equilibrium can also be explained with the help of a graphical representation. For example, I'm going to have two curves and a graph that is showing the concentration on y-axis and time in hours on x-axis. Here are the basically two curves or two lines you can say. One is going to represent the reactant. This is the line that is showing the change in concentration of the reactant with the change in time. The second one line that is starting from the zero is also showing the change in concentration of the product. This line that is rising from zero, it is going to demonstrate the change in concentration or increase in concentration with respect to the product, I mean yield that is being formed in this chemical reaction. You can see that in this picture that a time will come when these two curves become the flat. I mean, now they become flat. This is almost the flat portion of the reaction. So, what does that mean? It means that the reversible reaction is completed now. And beyond that level, you can say there is no change in the amount of the product, no more amount will be increased, and no more reactants are going to decrease anymore. So, actually, in fact, indeed, you can say that the reaction is completed now. And this stage is said to be dynamic equilibrium. At this stage, reactions keep on moving. I mean, reactants are going to change into the products, and reversibly, the products or the yield is changing back into the reactants. So this stage is the dynamic equilibrium. When these two curves becomes flat, that is the indication of dynamic equilibrium, that the stage of the dynamic equilibrium, the position of the dynamic equilibrium is achieved. With the help of this curve, we can also get other informations as well. For example, how much products have been made during the course of that chemical reaction. You can see it from the curve from the y-axis. Let's see over here. If I'm extrapolating this flat portion towards the y-axis, then almost you can say 0.68 moles per dm cube of the product have been made. Same is the case. I mean, the remaining reactant, the concentration, the quantity of the remaining reactant can also be seen with the help of this curve. Again, I'm going to extrapolate this flat portion of this lower curve, the curve that is showing the change in concentration of the reactants. And we can see that the remaining concentration is almost 0.26, almost roughly, you can see that. So number one, the change in concentration with the time that decreases always with respect to the time, and change of concentration or the concentration of the product always increases from zero, and it increases, then it becomes a flat portion. So these are the two typical curves. Those are showing the change in concentration of the reactant and change in concentration of the yield or the product. The third one, we can also, as I told you, we can also find the time limit. We can also find the total time taken for the completion of reaction. I mean, the time at which the dynamic equilibrium has achieved. We can also find it, but this time we are going to find it from x-axis, not the y-axis. And we can extrapolate this line towards the x-axis. I mean, that is the time for the completion of the reversible reaction. The next one, disturbing the equilibrium. When the reaction is achieved equilibrium, when reaction achieved equilibrium, then this equilibrium can be disturbed. It can be disturbed by concentration change or by change in concentration. It can be disturbed by change in pressure. It can be disturbed by change in temperature. So, by three ways, we can disturb that equilibrium. Equilibrium mean once again when the rate of the forward reaction becomes equal to the rate of backward reaction, to the rate of reverse reaction. Equilibrium of the rates. Rate of forward reaction is in equilibrium with a rate of backward reaction. I mean, both reactions, both opposite reaction are running with the same speed. Even same amounts are converting into the opposite direction. Equal magnitude of the reactant and product are converting forward and backward. So the conversion amount you can say is also same, and the speed of the both reactions, forward reaction and the backward reaction, is also same. When this stage is established, then after the second step is, or the after that step, we can disturb that position of equilibrium by changing the concentration. It will be disturbed by changing the pressure. It will be disturbed. And the third and the last one is the condition, that is temperature. By changing temperature, we can disturb that stage of equilibrium. So what will happen? The reaction will retaliate, will respond against this change. I mean, the position of equilibrium will shift either towards right or towards left to undo the effect of that chain. That is said to be Le Chatelier principle. Once again, when the equilibrium is disturbed, when the equilibrium is disturbed by any uh, parameters like concentration, pressure, and temperature, the position of equilibrium will shift towards right or towards the left to undo the effect of that change. So that is, this phenomena is said to be, or this phenomena is explained by Lee Chatelier principle. Now let's talk about the effect of concentration on the yield of a chemical reaction. Yield mean product once again. I'm having a closed container, and in this container, let's suppose there is the mixture of, or I'm putting N2O4, it's a liquid, and it is going to decompose into 2 mole of nitrogen dioxide gas. Basically, I'm going to divide this whole mechanism, this whole system into two parts. One is said to be the right hand side of the system of the equation, and this is said to be the left hand side of the system of the equation. Initially, I have started from N2O4, that is a reddish brown liquid. It decomposes itself into nitrogen dioxide. After some time, nitrogen dioxide again meet together. 2 mole of NO2 meets together to make N2O4 liquid back after some time interval. So this is one, the first one is the forward reaction, and the reaction that is going to start later on is said to be the reverse reaction. The color of this N2O4 is the reddish brown, that is reddish brown liquid, and nitrogen dioxide is the brownish gas, you can say. So if, let's suppose I'm going to add now, at this stage, if I'm going to add more nitrogen dioxide into this sealed container, if I'm injecting more nitrogen dioxide into this sealed container, the color will becomes more deeper, more reddish of this whole system, of this whole closed container. And reversibly speaking, if I'm going to add more N2O4 liquid into that container, then obviously the color of this whole container will be seen like the brownish color. So it means that upon the addition of, or upon the increasing the concentration of the any species, equilibrium shift towards the other side of the equation, other side of the equilibrium. How to report the answer? Let's see over here. On changing the concentration of the reactant or the reactants, basically, there is the disturbance of the equilibrium position. Change in equilibrium, change in concentration is associated with change in equilibrium. I mean, when we change the concentration of any sort of compound, any species, either it is present on the right hand side or on the left hand side, indirectly we are going to disturb, or we are disturbing the position of equilibrium. Then what will happen? This reaction will retaliate, will do something special, or it will respond itself. So equilibrium position will shift either towards the right hand side or towards the left hand side to undo the effect of that change. So, what is the final point? The basic point is it will shift toward that side where there is less concentration. As I told you, if I'm going to add more nitrogen dioxide, equilibrium will shift back towards N2O4 to where there is a less concentration of the N2O4. If I'm adding more N2O4, then equilibrium will shift toward the right hand side to make more moles of NO2, because comparatively, if we have increased the concentration of N2O4, comparatively, the concentration of NO2 is less than that of N2O4. So, when the equilibrium is disturbed by changing the concentration, equilibrium will shift towards that side where there is less concentration. Same is the case if I'm adding any sort of species like NaOH. NaOH is an alkali and it will consume all the nitrogen dioxide gas. For example, we have consumed all the nitrogen dioxide gas that was formed at the time of at the stage of dynamic equilibrium. Then again, this equilibrium will shift toward the right hand side. This equilibrium will shift toward the right hand side to compensate the lost quantity of nitrogen dioxide. It will shift towards the right hand side to compensate to make more nitrogen dioxide and to attain the dynamic equilibrium again. So, this is the attitude of change in concentration on the yield on the product of the chemical reaction. So, if we are going to remove this NO2, then this equilibrium, this reaction itself will shift towards the right hand side, its position will shift towards the right hand side, and it will make more and more and more and nitrogen dioxide. So yield will be increased, its product will increase, its quantity will be increased, and so on. The next one factor is effect of temperature on the yield. To know the effect of temperature on the yield, we should know the exo and endothermic nature of that chemical reaction. Exo and endothermic nature will decide the effect of temperature on the yield. Let's see over here. Once again, I am going to divide generally a chemical reaction into two parts. This time I'm going to write nitrogen plus 3 mole of hydrogen. Both are gases. They are meeting together. Initially, they react together to make 2 mole of ammonia. After some time, ammonia start to decompose and reverse reaction start, and it's going to make nitrogen and hydrogen back. A time will come when the rate of forward reaction, I mean the rate of formation of ammonia, that is equal to the rate of decomposition of ammonia. This stage is said to be dynamic equilibrium. And this reaction is basically exothermic reaction. This reaction is exothermic reaction. Exothermic reaction can be written as reactants goes to the product plus, we can write heat as a product. So basically, once again, this is the right hand side of the equation that is having ammonia and heat. This is the left hand side of the equation that is having reactants, nitrogen and hydrogen. Now, keep in mind one thing that is the important one. Basically, increase in temperature. Remember that increase in temperature will favor the endothermic side of the chemical reaction. Increase in temperature will favor the endothermic side of the chemical reaction. You know, this right hand side is exothermic side, I'm sorry. So it means that, as you know, it's a reversible reaction. If its right hand side is exothermic, so its left hand side will be endothermic. It will be endothermic. So this reaction is having two sides, imaginary, you can say that, and one is exothermic, other one will be the endothermic. So on increasing the temperature, Increasing the temperature will favor endothermic side of the chemical reaction. So on increasing the temperature of this whole container, of this sealed container, equilibrium will shift towards where there is endothermic side. I mean, increasing the temperature will lower down the amount of ammonia that was formed at the time of dynamic equilibrium. And reverse is true for lowering the temperature. Lowering the temperature will favor lowering the temperature. I mean, that was the increasing the temperature, and lowering the temperature will favor the exothermic reaction. Lowering or decreasing the temperature, decreasing the temperature. So decreasing the temperature will favor the exothermic side of the reaction. Increasing the temperature will favor the endothermic side of the reaction, and so on. Then once again, how to report your answer. First of all, check reaction is exo or endo. So you will write reaction is exothermic or it's endothermic. Then increasing the temperature favors the endothermic side of the reaction. I mean, right hand side or the left hand side. And reciprocally, you can say that decreasing the temperature will favor the exothermic side of the chemical reaction. Then the last one, equilibrium position will shift itself toward that side. I mean, it may be towards the right hand side, it may shift towards the left hand side. So accordingly, sometime yield will be decreased and sometime yield will be increased. So these are the basic points by which you can explain the effect of temperature on the yield on the product of the chemical reaction. The last one is effect of pressure on the heat. If the gases are present in the that chemical reaction, then there is the effect of pressure. If there is no molecule is the gaseous state, then there will be no effect of pressure on the yield of a chemical reaction. Once again, I'm taking a sealed container, and I'm going to divide imaginary into two portions. One is the right hand side and other one is left hand side. Once again, for example, I'm writing nitrogen gas plus hydrogen gas going to, first of all, they will meet together to make 2 mole of, I mean, ammonia gas. After some time, ammonia will start to decompose. A time will come when the rate of forward reaction will become equal to the rate of reverse reaction, and this stage is called dynamic equilibrium. After the arrival of that stage, you can disturb this equilibrium by changing the pressure. By changing the pressure mean you can change the volume, you can compress the volume of the container, or you can expand the volume of the container. So basically, the effect of pressure is going to based on the number of volumes or the number of mole of the gases on the left hand side and on the right hand side. Basically, moles are, you can say, the volume is important to see the effect of pressure on the dynamic equilibrium. Let's see over here. On the left hand side, 4 moles of gases. 4 moles of gases are there. On the right hand side, 2 moles gases are there. Now, once again, if we are going to increase the pressure, then equilibrium will shift toward that side where there are less number of mole, that is increasing the pressure. Increasing the pressure will favor less number of mole, the side where there are less number of moles. So, in this particular Haber process, by increasing the pressure, equilibrium will shift itself toward the right hand side and you will get more and more and more ammonia gas. So, increasing the pressure will favor the production of the formation of NH3. If you're going to lower down the pressure, then equilibrium will shift toward that side. Lowering the pressure, decreasing the pressure, decreasing the pressure, decreasing the pressure will shift the equilibrium towards where there are more volumes or where there are more moles of the gases. So there must be the gases. Number one, there must be the gases. Number two, you should check the moles on both sides. Moles on both sides. Number three, see the effect of increasing pressure. First, increasing pressure will shift equilibrium position towards less number of moles. So yield will be changed accordingly. That's all about today. Thank you very much. Have a nice day.